Hi, welcome back to this video series on quadratic residues. Today I'm going to apply quadratic residues concept and develop a crypto system called Rabin Cryptosystem. Okay, Michael Rabin is one of the computer scientists who invented this idea behind encryption based on the concept of finding roots in a composite group. Okay, so the idea is pretty novel. So suppose you have a composite number, say n equal to p times q. P and q are prime numbers, odd prime numbers, distinct prime numbers. So for this discussion purpose, I'm going to make some assumptions about p and q. P is, say, congruent to 3 mod 4, right? When you do p mod 4, you get 3 as a reminder. Essentially, that's the meaning of the statement. And the same with q as well. So both p and q satisfy this property that they are 3 mod 4. Okay, all right. So what is the idea behind Rabin's encryption system is that suppose you have a number x as a message you want to send to your partner. What you do is you send x square mod n to your partner. So n is the public key, right? Let's say Alice wants to talk to Bob. Bob would publish n, right? Here is Alice and here is Bob. Okay, who publishes n? Bob publishes n. Okay, n is public, p and q are private, so he publishes n. And what is Alice going to do? Alice is going to send a message x to Bob. So all she does is she computes x square mod n and send it to Bob. So Bob gets this y. Okay, what will Bob do? Bob has to find x, right, from y, but Bob knows p and q, so he will be able to find out the y. Essentially, that's the idea of this basic version of a Rabin algorithm, which is basically raw Rabin algorithm, because there's no protection against chosen plain text attack. I will talk about that later, but at this point, the math is the important part. Y equal to x square mod n, or y is congruent to x square mod n. What you're doing as Alice is, you have a message x, you take the square of that and take mod n and send y to Bob. Bob will apply the idea of reconstructing the square root. Basically, Bob will compute the square root of y, right, to find out the x. Basically, that's what Bob is going to do. So Bob is going to find some x such that x square is equal to y. That's the job of Bob. Okay. So how is Bob going to do that? Bob is going to apply this concept we talked about in the previous segment, right? He knows p and q. So all he is going to do is first he takes the y and he projects it to the mod p group and mod q group, right? So he's going to take his incoming y from Alice and going to put first into mod p and the mod q. And he will use Chinese remainder theorem to then find the square roots of y in mod n. Okay, so this is basically the idea. So we have explained in the previous segment how to compute the square root of a number in mod p and mod q. So that's basically the idea that Bob is going to apply. Okay, so there is one caveat you need to be aware of. Let's assume a very simple example. Let's say p being 3, right, and q being 7. Now, what is our n? N is 21 because we multiply p and q. Suppose, say, let's assume you are Alice, right? And Alice wants to send a number 4 to Bob as a secret. Okay, what will Alice do? Alice will compute 4 square, which is 16, in mod n, right? Mod 21. 16 mod 21 is 16. So she's going to send the 16 basically to Bob. Bob is going to get 16, but Bob has to find out the square root of 16 essentially. But square root of 16, there are 4 roots actually in mod 21. The square roots of 16 are 4 square is 16, and some non-trivial ones. 10, if you do 10 square is 100. 100 mod 21 is 16, and you can also check that 11 is also another square root. 17 is another square root. So there are 4 square roots. This is the property in a composite group. So if an element has a square root, there are 4 square roots. So Bob actually cannot tell with 100% precision which message out of these 4 messages was actually sent by Alice. So it could be 4, it could be 10, it could be 11, or or 17. So that's a big problem, right? You are getting some message, you have 4 possibilities, you don't know which one to pick. Okay, so that problem can be easily solved. I'm going to show you how to solve that in a moment. Basically, if X has some redundancy, right, Bob will be able to figure out which of the 4 messages, one of the 4 messages was actually sent by Alice. Okay, what I mean by redundancy is some kind of a pattern there, you know. The pattern could be the message is, or the secret is, something like that. So that the remaining 3 are totally useless, unreadable messages, only 1 is readable. Okay, that's basically what I'm trying to say. Okay, so let's take an example now. We tried a sample example here, right? Already P, Q, and N, tiny numbers. Why is this a secure system, by the way? It's a secure system because we don't know, as an attacker who's monitoring this traffic, is seeing Y. He knows Y and N, but he can't find X from it because attacker doesn't have P and Q. Okay, so the idea is that if you don't know the prime factors, it's difficult to compute the square root for large number N, not for tiny number 21, but in general for very, very large number like 2048-bit number or something like that. Another thing is that if you find a way to solve this, let's say you are given a Y and you are able to find an X such that Y equal to X square, actually your algorithm can be now used to factor the N into P and Q. So there is a nice reduction between solving this problem, meaning from Y finding an X, and factoring the number N. Okay, that's basically one of the appealing aspects of the Rabin algorithm, right? Michael Rabin is computer scientist with many interesting discoveries in cryptography and in algorithms. He has Rabin Miller primality tests and many more inventions. Okay, so this is the idea of Rabin algorithm, right? As a sender, you pick an X, you do X square, and you do a mod N. N is produced by Bob. N is the public key. N is the public key, right? P and Q are private keys. Bob will not publish that, of course. And what is the other important aspect is that it's difficult for an eavesdropper to compute the square root, right? So that is the assumption of this crypto system. Okay, now let's take a simple example and get us through this demo. So I'm going to take a simple example, right? What you're seeing is Python implementation. I quickly implemented this just for a demo purpose, right? Earlier we were talking about this thing. Let's run this one moment, right? I'll just rename it for a moment. Okay, so what if Alice is sending 16 to Bob? Bob cannot tell which one was sent. It could be 4, 10, 11, and 17 because all of them turned out to be square root of 16. Okay, so that's basically what I was telling earlier. Now let's consider the scenario that we are interested in, a much more serious one, not sending a 16. Let's do something more serious. Say, let me call this as just 2. We don't need this anymore. And now I will be using this function. Okay, so here is our regular main, and let me run it and then talk to you about it. So Bob publishes the private key. Oh, sorry. Bob computes the private key, publishes the public key. Of course, that will be dangerous to publish a private key. Okay, so what is Bob doing? Let me show you the details one by one. Bob computes. Maybe I should just comment this thing to get a clear output. I'm just using a 512-bit for a demo purpose. Of course, you will be using 2048 in real world. Just very quickly, you get the answer. Okay, so Bob publishes N, and Alice is picking a message. The secret message is, "How are you, Bob?" is the message Alice wants to send to Bob. And then, well, this is a text, so it has to be converted into a number. And that's basically, we are using Python for that purpose. So the string is getting converted into a number, encoded using UTF-8 format, and then we encrypt it. Okay, so what is encryption in this case? Encryption in this case is extremely simple. Let me show you what is encryption doing. Encryption function, remember, is nothing but square the number and take modulus n. That's basically the encryption function Alice will execute. And she's sending this encrypted version to Bob. We can also comment that because it's just gibberish anyways, right? And what will Bob do with it? Bob will decrypt it using his private key P and Q, right? And the incoming ciphertext from Alice. Okay. So as I mentioned earlier, there are 4 roots. We don't really know from Bob's perspective. Bob cannot tell which of the 4 elements that he got from the decryption process was actually the message sent by Alice. So what you're seeing now is that Bob is a little confused. He doesn't know which one is sent, but there is some redundancy we built in, right? We said the secret message is. So if you look at the output, Bob is seeing this, right? The first message is gibberish because he just has something like this. And second message also gibberish, third is also gibberish. And look at the last one. The secret message is, how are you, Bob? So if you build in some structure, like some kind of a header or something, it's very likely that out of the 4 message, one is in readable form. The rest are all completely gibberish. Okay. All right. So that's basically it. And I'm not going to talk to you a lot about the decryption process. Essentially, he takes incoming ciphertext and he computes the square root. That's basically what he does, right? Using his P and Q that he knows. All right. So what we learned, let me recap very quickly, is that we found a way to solve this equation, right? Y equal to x square mod n was solved. From y, we find a x because b meaning Bob, find a x because Bob knows P and Q. So if Alice was sending a secret x, Bob will be able to find the secret x. Okay, there's one caveat. There are 4 possible roots when this equation is solved, 4 roots for this equation. But if x has some kind of redundancy, some pattern, then Bob will be able to tell very precisely what was sent. Okay, that's really the beautiful idea behind the quadratic residue concept that we have been studying for a long time now. So, and there is a problem with this crypto system, by the way. Suppose you are an eavesdropper, okay, and you know that Alice will be sending either a message M1 or M2 to Bob. But you can now easily tell which message was sent by Alice. All the eavesdropper has to do is he can also do M1 square mod n, right? And M2 square mod n. And he can compare M1 square with Y and M2 square with Y. And if one of them is equal, then he knows which one was sent. So it's not really chosen plain text secure. But that's something I will talk about later in the next segment. This is a raw version of Rabin, right? It's a raw version of Rabin. Just to demonstrate to you the idea of quadratic residues and how this is helpful to construct a crypto system. Okay, all we are doing is basically, from Alice's point of view, pick a message x, square that message, take a mod n, and send y to Bob. Bob finds the square root of y, meaning if you multiply 2 times, you get x, right? That's basically what Bob is going to solve. And what else he's doing? Basically, he takes this n and put it into, he takes his incoming y and put it into mod p and mod q, and then he tries to find out the square root of this y and y in mod p, y in mod q. Okay, so a number when multiplied 2 times it gives y essentially in mod p and in mod q, and then he combines them using Chinese remainder theorem we talked about in the earlier segment. Okay. That's basically it. So we know how to use Rabin crypto system now, and we saw an interesting simple example. Okay, thank you very much.